So let's start with the following problem. Silence will continue to write. We are going to have a 24-volt source here, 24 angle 0 degrees volts. And just to be clear, we're going to start off in the frequency domain today. We're not going to bother going through converting to the time domain to the frequency domain because I think we've gotten enough of that to this point. Here we're going to have a 4 ohm resistor. Here is J 4 ohm inductor. A J 2 ohm inductor. Another 4 ohm resistor. A 10 angle 0 degrees volt source. A 3 ohm resistor. And a minus J2 ohm capacitor. And the quantity that we are trying to find is the phasor voltage Vx measured between that top right node and the bottom node. So for this particular circuit, probably a little bit more complex than you guys have seen in a little bit. That's okay. The only simplification that we could possibly do would be to combine that 3 ohm resistor in series with that minus J2 ohm capacitor into a single equivalent impedance. But other than that, we're stuck with what we have, right? So a circuit of this complexity isn't going to be able to be solved using the techniques that we developed or reviewed really in the last class. So we're not really going to be able to throw Kirchhoff's current law at it, Kirchhoff's voltage law, voltage division, current division, Ohm's law, things like that. Those are going to be parts of our analysis, but it's not going to be enough. We might be able to figure out a way to analyze the circuit using superposition and those methods. But if we're going to analyze the circuit twice, I say, let's just analyze it once and then use the computer to get us through the hard part. Okay. So because I'm trying to find a voltage here, I am going to use nodal analysis to solve this circuit. Okay. So what do you guys remember about nodal analysis? We got to set our ground. That is absolutely a great step. So Preston, tell me where you think ground should be. At the bottom. Sounds perfectly reasonable. Set my ground node here at the bottom. All right. What do I need to do next? Use it. So we're going to use Kirchhoff's current law, sure. But I would argue my next step should be to identify and label my different nodes so I know where I'm going to apply Kirchhoff's current law and all that kind of good stuff. So I like to use different colors to identify my nodes. So since I've made ground blue, I'm just going to go ahead and make this entire bottom node blue. Let's make this node here orange. This node up here red. This node here green. This node in the middle light blue, and this little node on the right hand side pink. And I am going to assign a nodal voltage to each one of these nodes. So I'm just going to start at the top. Let's call this node A, so it'll have a nodal voltage VA. This will be node B with a nodal voltage VB. Node C with a nodal voltage VC. Node D with a nodal voltage VD. Node E with a nodal voltage VE. So we're going to have a 5 equation, 5 unknown system. So for sure, a computer is going to be the way to solve this thing. All right. So did you guys learn about supernodes in your previous class? See a couple of people, I think, shaking their heads yes, and other people shaking their heads no. All right. So did you learn about what to do in nodal analysis when you have voltage sources? I'm going to assume that you worked a nodal analysis problem with a voltage source at some point. Was the voltage source always connected to ground or not? All right, so I might be confusing people, so let's look at some things here, right? So the first equations that I want to write are my voltage relationship equations, okay? So when I perform nodal analysis, I do it in a very specific order. And I do the things that I'm most likely to forget to do first. And the one thing that I'm most likely to forget to do when doing nodal analysis is to write my voltage relationship equations, okay? So what I mean by a voltage relationship equation is I'm going to try to relate all of my voltage sources to my nodal voltages, right? So let's start with that 24 angle 0 degrees volt source in the top left, right? So 24 angle 0 degrees volts is going to be equal to some combination of voltages, right? Or some combination of nodal voltages. So how I figure this out is I simply take the voltage at the positive polarity terminal. So what's the nodal voltage at the positive polarity terminal here? VA. Absolutely right. So the one at the positive polarity terminal gets a positive sign, and the one at the negative polarity terminal gets a negative sign. So what's my nodal voltage at my negative polarity terminal of this 24 volt source? VC. So I can say that 24 angle 0 degrees is simply VA minus VC. Okay. We can do something very similar here for our 10 ohm, excuse me, our 10 angle 0 volt source, right? So 10 angle 0 degrees volts. What's my nodal voltage at the positive polarity terminal of this source? VD. And what's my nodal voltage at the negative polarity terminal? Ground, so 0. So I'm just going to say that 10 angle 0 degrees is equal to VD. So that's how I write my voltage relationship equations. Okay. So I'm going to take Matthew's suggestion, and we're going to start writing Kirchhoff's current law equations, and we're going to start at node A. We're actually going to run into a little bit of a problem here, but we'll talk our way through it in just a moment. So if I were you, would not write this down. I know some of you have started, maybe I should have prefaced that. There's intentionally, it's not going to be a mistake in this equation, but there's going to be a problem in this equation, okay? So we are performing Kirchhoff's current law at node A. So that means that I'm going to be adding together this current and this current, because those are the two currents that are leaving node A. I'm going to add them together and set them equal to 0. The current flowing to the right through my 4 ohm resistor is going to be VA minus VB over 4 ohms. And then I'm going to add to that the current flowing down through that voltage source. How do I express the current flowing through a voltage source in terms of my nodal voltages? So I'm doing Kirchhoff's current law and saying that the currents that are flowing out of that node are positive and that the sum of them will equal to 0. So the problem that I have here is that this is a voltage source. For a voltage source, we know that there is a fixed amount of voltage across its terminals, and any amount of current that needs to flow can flow. there is no relationship between that voltage source and the current that's flowing down through it that I can express in terms of my nodal voltages, right? So this is where the concept of a supernode comes in. If we were to, let's just call this I-24 down is equal to 0 for now, okay? Over here, I'm going to write a KCL equation at node C. So that's going to be this current plus this current plus this current, right? Let's do the ones that we can take care of first. The current flowing to the right through our J2 ohm inductor is going to be VC minus VD over J2 ohms. My current flowing down is going to be VC over 4 ohms. And then my current flowing up, I'm going to have to call I-24 up. And this is equal to 0 because I don't have any relationship that I can express, right? So this expression right here, this KCL at C equation, is the current flowing to the right out of node C, plus the current flowing down out of node C, plus the current flowing up out of node C. So this is going to seem like a kind of an odd question, but what would happen if I added these two equations together? So what happens if I have a current flowing up and I add to it the exact same current flowing down? They cancel each other out, right? So if I add these two equations together, I'm going to call this KCL at supernode AC, okay? And so that's going to look like VA minus VB over 4 ohms plus I-24 down plus I-24 up plus VC minus VD over J2 ohms plus VC over 4. What is this going to be equal to? So my equation on the left-hand side is equal to 0. My equation on the right-hand side is equal to 0, and I'm simply adding these things together. So what's 0 plus 0? 0, right? And this guy right here and this guy right here wind up canceling each other out. And so we now have one equation, and effectively what we've gotten is the currents leaving this big thing, a supernode, that contains both nodes A and C, okay? So anytime we have a voltage source that isn't connected to ground, and that's very, very important. Anytime we have a voltage source that isn't connected to ground, we can draw a circle around the voltage source and then just add up the currents that are leaving that circle as our KCL equation, because we know that the currents flowing through the voltage source are going to wind up canceling each other out anyway if we added them up individually. Okay, so that's how we apply a supernode here. The reason why we won't do that for a voltage source that's connected to ground is because we never write a KCL equation at our ground node. So we never figure out the currents that are flowing out of ground, because that's redundant information. Okay. So we'll practice with that a little bit more. If it's new to you, it's going to seem weird. And so I want to make sure that we're all on the same page. But we now have this first equation. Here's our second equation. Here's our third equation. So we should be expecting 2 more equations for this system because there are 5 nodes, right? So we have a KCL equation for nodes A and C. Now let's write a KCL equation for node B. So I want you guys to tell me what's going on here. I'm going to be adding these currents together. Okay, let me scroll down here. Yeah. So let's start with the one directed to the left through the 4 ohm resistor. How am I going to write that current in terms of my nodal voltages? Exactly right. VB minus VA over 4. Somebody else tell me what my current flowing down through the J4 ohm resistor is going to be, or J4 ohm inductor. Exactly right. And then somebody else tell me my current flowing to the right through the 3 ohm resistor. Exactly correct. Is equal to 0. Here is our 4th equation. So we need to come up with one more equation. Okay. So we're not going to write a Kirchhoff's current law equation for node D. Because once again, we have a supernode. Anytime we have a voltage source, we're going to have what I'm calling a supernode. But since this supernode contains ground, I want to repeat this again, we do not write a KCL equation at this supernode. So the only other node that's left is node E, right? So we're going to write a KCL equation there. So that's going to be this current up plus this current down. So somebody tell me what my current flowing up through the 3 ohm resistor is going to be. Exactly right. And my current flowing down through the minus J2 ohm capacitor. VE over negative J2. Absolutely correct. So we have 5 equations and 5 unknowns. So we're now ready to throw a computer at this thing because solving this by hand would be absolutely and utterly terrifying. Okay. So I'm going to open up MathCAD. So for those of you who also remembered to download MathCAD and all of that kind of good stuff, you might be seeing this little error thing right here that says full functionality, 27 days remaining. That's because Louisiana Tech University, or actually Miss Ashley down the hallway, is currently in negotiations of getting our license renewed for another year. So that process takes a little bit of time. But I am very positive that before these 27 days run out, they will come to an agreement on the pricing and we'll all have access to MathCAD for another year and all that kind of good stuff. The reason why we need a licensed version is so that we have an access to the solve block, because the solve block is what we're going to use to solve a system of equations, okay? So I'm going to put a solve block here on my page. And I'm going to make it a bit bigger, okay? All right, so a couple of things here. I personally choose to use units in all of my calculations that I do in literally everything. If you're going to use units, that's great. If you're not going to use units, that's also okay. But you either need to use them, like use all of the units, or use none of the units, because if you forget to put units on something, if you're trying to use units, MathCAD is going to freak out, okay? So either use units or don't, but you can't mix and match or things are going to go poorly, all right? So we have 3 different sections here. We have a section for guess values. So that's where we're just going to give an initial guess to the computer as to what we think the answer might be. Then we have our constraint sections. This is where we enter in those equations that we just developed. And then we have the solver section, which is where we tell the block to solve the system of equations that we've given it, okay? So in our guess value section, we're going to write a simple expression here for every one of our variables, VA through VE, and we're going to set it equal to something. And it's literally just a guess. So for the most part, the value doesn't matter. So I'm going to say VA, and I am using subscripts just like I did when we were writing everything out. If you want to use subscripts, that's perfectly okay. To do that, you press the Control- key, okay? And then the letter that you want. And then now I'm going to do Shift::. So this is a specific type of equal sign. MathCAD has 3 different equal signs and they all mean 3 different things. This is effectively the equal sign that is used to say, set this variable equal to some number, okay? So because we're dealing with complex numbers, I'm going to open a parentheses here, and I'm going to say 1, I'm going to do 1 angle 0 degrees. Let me get this out of the way so that we can see things here. So if we look in this operator section, and we go down to engineering, there is an angle operator, but we can also see that there is a keyboard shortcut of Control-Shift-P. I am too lazy to go up to this menu and click that button every time. So from here on out, I'm going to just hit Control-Shift-P to give me the angle operator. While we're here, I want you to notice there's also the degree symbol in this particular area of the page. And there is not a keyboard shortcut, so we're going to fix that in a moment, okay? So Control-Shift-P gives me my angle operator. Now I'm going to do 0. And as it stands at this exact moment, this is 1 angle 0 radians, which really wouldn't matter for us, but I like to work in degrees. And so I'm just going to type in DEG to let the computer know that that angle has units of degrees. Outside of my parentheses, I'm going to give this, oops, I went too far, the units of volts, because this is a voltage. You don't have to use the units if you don't particularly want to. Okay. I'm going to do a similar thing for VB through VE, right? So V, Control -sign B, Shift semicolon is equal to, open parentheses 1, Control-Shift-P, give me my angle sign 0 DEG, volts. Over here, I'm going to do it for VC. VC is equal to 1, and 0 degrees volts. And if you guys have any questions about anything, please, please, please let me know. So are we caught up for the most part? All right. So now we're going to start entering our constraints. These little brackets on the left-hand side will move around. So it doesn't particularly, it doesn't particularly matter that I am going to start entering an equation in this middle area that doesn't have a type associated with it. As soon as it figures out that I'm writing a constraint equation, it'll extend that bracket to include this thing, okay? So for my constraint equations, I'm just going to go back to the equations that we developed, and I'm going to put them in, right? So my first constraint equation is going to be this first voltage relationship equation. 24 angle 0 degrees volts will be equal to VA minus VC. So I'm just going to open my parentheses, 24 control shift P angle degrees volts. And for this equal sign, I'm going to press control equal. So this boldface equal sign is saying whatever is on the left-hand side of the equal sign must equal whatever is on the right-hand side of the equal sign, okay? And in this case, that is VA minus VC. Like so. My second equation was 10 angle 0 degrees volts, control equal. And I want to say that was VD, but let's double check just to make sure. Yep. And so I've got two of my constraint equations written. Let me know when you guys are done with these and we'll move on to the next ones. And again, if you have any question, yes, sir. Control equals. So I use shift colon in my guess values section, and I use control equal in my constraints section. So let me just show you guys something really quick here. I'm going to replace this equal sign with a shift colon sign, or at least I'm going to try to. It's being difficult. Why is it being so difficult? All right, I'm gonna have to write this from scratch apparently. Oop. This is weird. It's literally not letting me do it. What I was going to show you effectively is that if you put the wrong equal sign somewhere, it's going to make the different sections of the solve block overlap. And so that's a good indicator that you've put the wrong equal sign somewhere. But for whatever reason, my computer is being finicky right now, and it's not letting me put the wrong equal sign here, which it should be. But anyway, all right, so we have these two constraint equations. So let's work on this next thing. So we're going to write this KCL at supernode AC equation. We're not going to put this plus I-24 minus I-24 thing. Those obviously cancel out. So we're just going to throw that part out because that would require us to introduce another variable in our guess section anyway. So VA minus VB over 4 ohms is our first term. So V underscore A minus V underscore B divided by 4. All right, so to get the unit of ohms, again, there are multiple different ways to do this. We could go into the symbols menu and go to uppercase Greek so that we have the ohm button or the capital omega button. We could also go into this units thing here and scroll way down to resistance and find the ohm symbol there, but there is a keyboard shortcut, so that's what I'm going to show you guys, okay? If I do Shift W, I get uppercase W, okay? And then Control G converts that uppercase W into a Greek letter. So Control G is converts to Greek. So the reason why uppercase W is capital omega is because lowercase w looks like lowercase omega, right? So lowercase w looks like lowercase omega, so uppercase w gives you uppercase omega, which is the ohm symbol. So that is our first term. Then we're going to have VC minus VD over J2. Is that positive J2 or negative J2? Positive J2. All right. So there is a particular syntax that we're going to need to use here, much like in your calculators. J2 is going to cause it to freak out. 2J is going to be perfectly acceptable, right? So 2J. And then I'm going to multiply this by the unit of ohms, okay? So the reason why I'm doing that, just to be really clear here, if I type in 2J and then a W or any other character, my J became italics. I don't want that because that's not the imaginary operator that we're using, right? So I need to write 2J times omega is letting this know that this is 2J ohms of impedance. Or don't use units and then it's just 2J. Then we have VC over 4 ohms. And this is going to be control equal to 0, again, because this is another one of our constraint equations. So enter this one in. If you have any questions about literally any part of it, please, please, please let me know, and I would be happy to help. Also, I'm obviously recording all this stuff, and as soon as I leave this class, I'm going to start working on uploading our last class meetings video and then this video so that you guys have access to them ASAP so that you can work on your homeworks and all that kind of jazz. So let's go ahead and work on our 4th and 5th constraint equations here. So that's going to be our KCL at node B equation and our KCL at node E equation. So VB minus VA over 4 ohms. Plus VB minus VD over 4J times, what the heck, ohm plus VB minus VE over 3 ohms equal to 0. Just because these are overlapping a little bit, I'm going to move this down. And then I'm going to have my last constraint equation, E minus B over 3. Plus E over minus J2 is equal to 0. I have all my equations written. So once we're to this point where we have all of our guess values established, all of our constraint equations written, now we can solve things, okay? So to solve this system of equations, what I'm going to do is I'm going to go over here to the matrix tab. I'm going to give myself a matrix, and it is going to be a 5x1 matrix because there are 5 different variables that I'm solving for: VA, VB, VC, VD, and VE. And I'm just simply going to move this out of the way down here. In this matrix, I'm going to put VA, VB, VC, VD, and VE. And I am going to shift colon equal. So I'm going to set this matrix equal to find open parentheses VA, VB, VC, VD, and VE. And press equal, and it spits out a bunch of complex numbers. So let me know when you're at this part, and then we'll talk about things here real quick. The matrix on the left, go to the matrices tab, and then the insert matrix button on the far left, and go to the drop down menu. It's going to be a 5x1 matrix. You go to that little point. Did you use the one that I put on blue? So use that real quick, because we'll have a little thing that tells you all the things that are. That's all. 138.7.1.17. Go back. Is your product Saturday or also looks like you're using all that signal. It doesn't matter. It should be active for all of them. Look anywhere else. And put anywhere in here. Now there's all block. The problem is, if you wrote all that stuff outside of the salt block, you have to literally rewrite it and drag it inside. All right, so how many of you guys have gotten to this part right here? Yes, sir. Are you raising your hand that you've got? Okay, sorry about that. Yeah. So these complex numbers that are written here are obviously in rectangular format and they're using I. Okay, so we want to switch this to something that we're used to. So if we go over here to the math formatting tab, right here, and we click anywhere in this answer box, this little thing right here says complex values, and it's a drop-down menu. So we can make MathCAD give us our answer in 5 different complex number formats. The first option is rectangular with I as the imaginary operator. The second option is rectangular with J as the imaginary operator, which is what we're using for rectangular numbers. Then we have polar form with the angle expressed in pi radians, polar form with the angle expressed in radians, and finally, polar form with the angle expressed in degrees, which is what we'll typically use. So if I press that button, it simply converts everything. There is still something a little bit wonky here. If we look at VD, it says 10 angle negative 5.789 times 10 to the minus 33. 10 to the minus 33 is a incredibly small number, right? Like ludicrously small. That's just MathCAD freaking out and not saying 0 because it's being dumb. That number is effectively 0 because it's 0.0000 blah, 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 30 something times 5.789. It's 0. Okay. So if you ever have a number here with an exponent probably greater than or more negative than 10, call it a 0 and call it a day. Okay. So we now have our complex numbers written in the format that at least I prefer, but we haven't exactly solved the problem. Okay, so let me explain by what I mean by that. If we scroll up here, our goal was to determine what the quantity Vx is, right? We haven't done that yet, but we can write a simple equation to get Vx in terms of our nodal voltages. So what should that equation be? So I'm saying Vx will be equal to some combination of our nodal voltage. So what's the nodal voltage associated at the positive polarity terminal of Vx? VB. What's the nodal voltage at the negative polarity terminal of Vx? The negative polarity terminal down here, by the way. Ground, so 0. So Vx is just equal to VB. Yes, sir. Sure.
I appreciate it. Mm-hmm. And this is going to be on Moodle, the recording for this class?
Yes.
Okay.
So Vx is exactly equal to VB. So we can go in our MathCAD sheet. We could literally look and just say, well, VB is 17.405. Or because I am this lazy, I will come in here and I will say Vx is equal to VB, and then it gives me the answer in rectangular form, which I don't like. So I make it spit it out in polar form so that there's no ambiguity. The reason why I store all of these values in that matrix is so that I can mess with them outside of the solve block. Okay. Everything inside of the solve block is only what's inside the solve block unless we store it somewhere to be used outside. Kind of like you're storing global variables and all that kind of stuff when you're programming an Arduino and all that jazz. The math formatting tab. Down here where it says complex values, or you can see where my mouse is up there on the screen. And then the bottommost option is for polar form with the angle expressed in degrees. Yes. So let me look at what you got. Probably. Forgot volts here. So if you forget even one single unit, it's out. Now, it's easy to say, shut up, watch. I did not. I'll look into that, or maybe I'll make you do it. Yes. So that's a very good question. So what this gentleman asked is, for the guess values, do we always want to use one angle 0 degrees? So let's scroll up to the top and let's screw around with the guess values real quick and see if anything happens. And the short answer is, for this particular system, it shouldn't. Right? Let me make sure I'm not telling tales out of school here. So 29.9 angle negative 16.633. The only thing that's changing when I change this guess value, and should be when I change any of them, is the representation of that 0 thing, right? So it's now a different number times 10 to the negative 33, okay? What those guess values are used for is if you're trying to solve a polynomial that has multiple solutions, then it will give you the answer that is closest to that guess value. Because none of these are polynomial relationships, it's going to give you the same answer regardless of what your guess value is. At least it should. If it ever tells you that it can't solve it for some reason, then just play around with your guess values a little bit and it should find something. So if it tells you that there's no solution, that usually means there's a trivial solution with everything is 0 and you need to change a couple of things and it'll find it. For the most part, it shouldn't be an issue. Using one angle 0 for all of these voltages or one angle 0 amps for currents should get you through for 99.9% of the stuff that you're going to be doing here. All right, so we've solved a problem using nodal analysis and MathCAD. Let's take a crack at a problem using mesh analysis and also MathCAD, just so we're sure we know how to do all that as well. All right, so our new circuit that we're going to take a crack at is this guy. And our goal here is going to be to solve for this current IX flowing through the J2 ohm inductor from right to left. So since we're using mesh analysis, I'm going to define my mesh currents. You guys might have heard of this as loop analysis. It's the same thing to me. So I'm going to call this loop IA. Here's IB. And here's IC. So this one should be a little bit easier to do. We've only got 3 unknown quantities to solve for. Okay. The first relationship that I write when I'm doing mesh analysis is always any current relationship. So effectively, for every current source I have in my circuit, I can write a current relationship. So in this case, I am trying to relate 3 angle 10 degrees amps to, I guess I don't really need these parentheses, some combination of my mesh currents. So do you guys have any idea what this relationship might be? So which one of these 3 mesh currents even flows on the same branch as the current source? Let's start there. IC, okay, that's the only one. So IC is going to be related to that 3 angle 10 degrees amps in some way. So I'm going to put IC right here. All right. Now, does IC flow in the same direction or the opposite direction? The opposite direction, so I need to put a negative sign. And there's my current relationship. If I had a current source in the middle of the circuit, so just for the sake of argument, let me throw a current source right here and just say that this is a 5 angle 0 degrees amps current source. What would my current relationship for this guy be? Is equal to 5 angle 0. 100% correct. So the current flowing in the same direction minus the current flowing in the opposite direction is equal to the current source. 100% correct. Okay. Just wanted to make sure you guys were aware of that in case it shows up in your homework or something. All right. So we have our current relationship equation here. Now we can start writing our Kirchhoff's voltage law equations for our 2 loops. Yes, ma'am. Where's the what? There isn't a ground because we aren't doing nodal analysis. So we can choose any node to be ground. It's not going to show up anywhere. Yep. So let's do KVL around mesh A. Okay. So somebody tell me what my Kirchhoff's voltage law equation should look like here. And I choose to start at the bottom left-hand corner of my meshes, just for sake of argument. So I'm starting at the bottom left-hand corner and I'm just following IA around its clockwise path, okay? So what's the first thing I see as I travel clockwise around that leftmost mesh, excuse me. I see the 12-volt source. That's the first thing I see, right? Since I see the negative polarity terminal first, I'm going to have negative 12 angle 0 volts. What's the next thing I see? The 3 ohm resistor, all right? Exactly right, IA times 3 ohms. What's the next thing I see? J2 ohm resistor, okay. Or J2 ohm inductor. That's also going to be multiplied by just IA. Right, so I'm following IA around. What's the next thing I see? It does branch, but we're following IA. So at this point, let me write this in purple, right? So we've gone through the 12-volt source. We've gone through the 3 ohm resistor. We've gone through the 2 ohm resistor. And now we're coming down this way. So we're going through the J3 ohm inductor, right? Exactly correct. IA minus IB. So the total current flowing through that one element is the difference of those two mesh currents. Exactly right. And then we see what? +6 angle 0. Absolutely right. Got this equal to 0, and we're done with this particular mesh. Right? Now we're going to have our KVL equation around mesh B. So the first thing we see is what? -6 volts. Absolutely correct. Because it goes in the negative. I mean, so we're just paying attention to all the polarities here. Okay, so let me explain what I mean by that when we're looking at these things. Okay, so what we've actually done with all of these impedances is we've assumed a polarity. Okay, let me use this color. Okay. You would have to flip literally every one of the signs, right? So when we wrote our KCL equation around mesh A, these are the polarities that we were using, okay? We didn't explicitly state anything here, but we were assuming that our mesh current IA is flowing into the positive polarity terminal so that everywhere we have an IA, we have a positive sign, and everywhere we have a current that's flowing in the opposite direction to IA, we have a negative sign. A consequence of that is that when we see the negative polarity terminal first, we need to add a negative sign. Just like on the 6-volt source, we saw the positive polarity terminal first. So we used a positive sign. And we're just doing the exact same thing around this second mesh, right? Because we're going in the opposite direction, now we see the negative polarity terminal of the 6-volt source first. So that's why it's -6 starting off our KVL around B equation. Okay. So what do we see next? All right, and that J3 ohms is going to be multiplied by what total current? IB minus IA, right? So now that we're following IB around, we are expecting IB to have the positive sign and anything opposite IB to get the negative sign. So IB minus IA, absolutely right. What do we see next? I disagree. We're following IB around its path. Yeah, so the 4 ohms. Yeah, so now we are up here through the 4 ohms. Absolutely right. And what current does the 4 ohm resistor see? just IB. Since it's on the edge of the circuit. And then lastly, we're going down through the capacitor. So that's going to be what? So negative J2 ohms times, I believe you said B minus C, which is absolutely correct. Is equal to 0. 1, 2, 3 equations. We have 3 unknowns, so we're good to go. Put things in a MathCAD now. So I'm just going to go to a new thing here. Start this process, right? So I'm going to come down here. If I can find my cursor, there we go. And I'm going to put a new solve block in. This time my guess values are going to be for currents. So I'm going to have 1 angle 0 degrees amps. So IA will be equal to 1 angle, oops, didn't hit control. Once I get those guess values put in, then I'm going to start writing my constraint equations. So I'm going to start with my first one that was 3 angle 10 degrees amps. Control equals negative IC. Then my next equation, negative 12 angle 0 degrees volts plus 3 ohms. So here's something that I want to point out really quickly. Sometimes MathCAD freaks out a little bit with parentheses. So whenever I'm going to multiply two things in parentheses, I'm going to make sure that I explicitly use the multiplication sign. What MathCAD sometimes does is it treats it as a function of whatever is inside one set of parentheses, which is not remotely what we're looking for. So if we remember to explicitly tell it, hey, multiply these numbers, we're going to be okay every time. So in this case, that should be 3 ohms times IA, I believe. Plus 2J ohms times IA plus 3J ohms times IA minus IB plus 6 angle 0 degrees volts. Control equals to 0. Now for my next equation, negative 6 volts plus 3J ohms multiplied by IB minus IA plus 4 ohms times IB plus minus 2J ohms times IB minus IC. Control equals to 0. I've got my 3 equations in. So I'm going to put my 3x1 matrix down. convert my results to polar form. And the IX current that I was looking for is just negative IA. So once again, if you have any questions about any of this, how to put it in or anything, I'm happy to help. If not, this is what I had wanted to talk about today. We have reviewed nodal analysis, we reviewed mesh analysis, and we have used MathCAD to solve systems of equations using complex numbers. So you are free to start on your in-class assignment whenever you feel you're ready. And by all means, ask questions if you have some, okay?